This is a demo of standing waves. When a wave reaches a boundary, it may result in a reflected wave, that is, a wave of similar properties traveling in the opposite direction. Under the right circumstances, the combination of original wave and reflected wave can yield a standing wave. The animation shows a blue wave traveling to the right and a red wave traveling to the left, with the resulting standing wave shown in black, then seems to oscillate in place. The red dots correspond to positions known as nodes that do not move at all. A wavelength is the distance along a wave before it repeats itself. Note that the distance between two nodes is half a wavelength. In this demo, an elastic cord is tied to a ring stand on one end and to a mass on the other. The cord is draped over a pulley, and the mass's weight provides a tension in the cord. Close to the ring stand, a speaker drives the cord at set frequencies. Some of these frequencies yield standing wave patterns in which the left-moving and right-moving waves interfere constructively. We are looking for standing wave patterns in frequency range between 20 and 50 Hz. This is 20 Hz. 21 Hz. 22 Hz. We see a standing wave pattern at 22 Hz. 23, a little bit left of the standing wave pattern, but it's going away. 24, 25, 26, 27, 28, 29, 30. At 30 Hz, we have a new standing wave pattern. 31 Hz, 32, 33, 34, 35, 36, 37, a new standing wave pattern at 37 Hz, 38, 39, 40, 41, 42, 43, 44, 45, a standing wave pattern at 45 Hz, 46, 47, 48, 49, 50. For frequencies leading to standing waves, we can measure the corresponding distance from one node to the next. That data is displayed here. Note that as the frequencies increase, the distances decrease. As seen previously in the animation, the wavelength is twice the distance between adjacent nodes. This table shows the data with a column for the wavelength added. The speed of a wave can be calculated by multiplying its frequency, that is the number of cycles per second, and its wavelength, i.e. the distance associated with one cycle. Here we have added a column to the table with a wave speed calculation. Note that the speeds are consistent, all falling between 18 and 19 meters per second. According to theory, the speed of a wave on a string depends on the linear density of the string and the tension in the string. This is why, for instance, guitar strings come in various thicknesses, and tuning is done by adjusting the string tensions. More specifically, theory says that the speed of a wave on a string is equal to the square root of the tension divided by the linear mass density, where by linear mass density we mean the mass of the string divided by its length. The tension was caused by a 0.3 kilogram mass, which thus has a weight of 0.3 times 9.8 meters per second squared, or 2.94 newtons. The mass of the elastic cord was 0.0145 kilogram, and its length was 1.79 meters, leading to a linear mass density of 0.00810 kilograms per meter. Using these tension and density values in the speed calculation yields a speed of 19 meters per second, consistent with the result obtained using the frequency and wavelength data.